Okay, hello everyone, and welcome to this APS webinar. A quick reminder before we get started, if you want to hear about future webinars, make sure that you're on our email list. You can sign up at aps.org/careers/guidance/webinars. APS webinars are brought to you as a service of the American Physical Society, connecting you with the expertise of individuals who can offer insight into physics careers, educational programs, and professional development for students, working physicists, and educators. Today's webinar is being recorded, and everyone who registered will receive a link to the recording. If you have any questions during the broadcast, please type them into the question box that is actually located on your screen, and we will get to your questions towards the end of the presentation. We will leave an ample amount of time for questions, so never fear. I'm Crystal Bailey, and I'll be your moderator for today's broadcast, where we'll be talking about tips and strategies for acing the Physics GRE. Many physics students are intimidated by the prospect of taking this exam. They want to know what to expect and what strategies will give them the best edge. Fortunately, GRE prep course leader Jeremy Dodd is here to describe the content and format of the Physics GRE Subject Test and provide you with these tips and strategies to best prepare for the exam. Jeremy Dodd is Senior Lecturer in Physics at Columbia University. His research background is in experimental particle physics, performed largely at the European Laboratory for Particle Physics, CERN. He currently serves as Director of Undergraduate Studies in Physics at Columbia and has been running a Physics GRE prep course there for several years. Before we get started, I assume everybody can actually hear me, but do me a favor. You should all have an ability to, quote, raise your hand. If you hear me, can you please raise your hand? Yes. Okay, fantastic. I'm seeing a bunch of hands go up. Okay, great. So, Jeremy, then, I will turn it over to you. Take it away.
Thanks very much, Crystal. Welcome to everyone who is now on the webinar. Very happy that you've taken some time today to join us for this Acing the Physics GRE session. Okay, so we're planning on going for about 35 minutes. I'll be showing some slides. The first half of the presentation will be just general advice, tips about getting ready for the GRE, and then the second half will be running through some sample problems just to go over some of the sort of approaches that might help you when you come to take the Physics GRE yourself. As Crystal said, we're planning on keeping a good amount of time at the end for questions. We should finish the formal part of the presentation around 3:35, 3:40, so there should be plenty of time for questions at that point. So please, if you would, just hold your questions until then. Okay, so first thing I would say is for those of you who are looking at taking the Physics GRE this coming fall, whether it's in September or October, I very much hope that you're already well underway with your preparations. One of the things we'll talk about is the benefit of getting started early. So I hope all of you are already going back and reviewing material from your undergraduate courses. Okay, so let's take a look at the slides. The first few things are more focused on the logistics. A little bit about the GRE itself, test-taking strategies, and getting ready. I will go through this at a fairly fast pace. You'll be able to go back and look at these resources offline after the fact. And much of what I'm saying in the first few slides you'll find also on the Educational Testing Service, or ETS, website. So I will go fairly quickly. This initial information is important, and I very much encourage you to take the time to look in detail at the ETS website and really make sure you know exactly how every aspect of the GRE works. So let's get underway. Okay, so the subject GREs, physics being one of them, of course, they're offered 3 times per year. The current scheduling for those 3 offerings is September, October, and April every year. Many of you are probably preparing already for this coming fall, so September and or October, and you'll see the dates for the exams this year. You'll see I put a footnote on the October exam date. That was actually recently moved a little bit earlier than it had traditionally been to make sure that there was time available for your results to get to the grad schools you're applying to. Seniors are usually taking the September and or October test. I can make a quick comment about that. Certainly with my students here at Columbia, I encourage students to certainly consider taking the test more than once. And if you are taking it in the fall of your senior year, it's definitely worth thinking about taking it both September and October. Then you have 2 shots at it, and as I'll mention in a moment, you can choose which results you want to send to the grad schools you're applying to. Some juniors may like to take the test the April of junior year. Again, good idea to get a sense of what actually the exam is like and sort of a warm-up, if you will. You may take the test multiple times. There's a score select feature now for the GRE, which again is a relatively recent addition. That allows you to select which test scores you want to send to a given institution. So again, take a look at the ETS website for that to understand exactly how that works. And of course, you'll need to choose a convenient test location. As we find here in New York, sometimes some of the locations fill up quickly, so try and make sure you make your reservation for your exam early so that you don't have to go further afield. Okay, so as I mentioned, ETS, Educational Testing Services, administers the exam. Please take a look at the website that you see on the slide there. Lots of really great information. You can register online, which is probably by far the most common option, or by mail. And you'll find typically that the standard deadlines are about a month ahead of the test date. There's a grace period of a week where you can still apply with a slightly higher penalty fee, but make sure you've got this well in hand. It's not cheap, unfortunately. The test fee is currently $150, which includes sending results to up to 4 schools. You can request additional schools for $27 each. But I should mention that you can also request fee reduction in case of hardship. And again, there's a URL to take a look at that to see if you can benefit from that option. There are health and disability related accommodations for students that request them. And again, please take a look very carefully, go through all of the pages there to make sure you understand how the registration works, how the notification of results works. The timing of that turns out to be quite important. Okay, so what about the test itself? The format of the Physics GRE has really not changed over many years. So it's paper-based and is a rather well-defined multiple choice format. All of the ones I've seen are exactly 100 questions. So I looked this morning just to see at the ETS documentation, and they say about 100. But let's assume 100 questions. You have 170 minutes for those 100 questions. So of course that corresponds to about 1.5 minutes per question, not a lot. You are not allowed to use calculators, but you will see at the start of each exam, and hopefully all of you have seen some sample exams at this point, there's a short sheet of constants and a very few formulae given at the start of the exam paper. And a comment that I'll make here already is, in terms of optimizing your time during the exam, you certainly will benefit from remembering fundamental formulae. In general, that's probably not something that physics instructors sort of recommend a lot. We much prefer that you are able to derive things, but in this context, I actually think it's very helpful to remember fundamental formulae. So if you can do that, all the better. Emphasize, again, you want to be fully familiar with every aspect of the exam well in advance of the test. And what is it testing? Well, it's testing key areas of undergrad physics. ETS says really it's looking at testing the first 3 years of a typical physics major curriculum, and I think that's about correct. And in terms of resources, which I'll talk more about in a moment, I find that your coursework itself and the course textbooks are probably your first resource in terms of preparing, but of course actual practice with the tests is, if not more important, at least as important, and we'll talk more about that in just a moment. Okay. So, many of you will have discovered, hopefully, the 5 sample Physics GRE exams that are readily available. ETS itself has just the latest, the 2008 sample test, but you will find fairly quickly with a search online the other 4 earlier tests. So you want to have all of those 5 essentially available, and I strongly recommend that before you take your exam, you've gone through all of those 5 tests. I find that it's helpful to take a first trial test under what I'll call test-taking conditions. So 3 hours, quiet place where you're working as though you were taking the exam, just to give you a sort of calibration so you know how you're doing, your strong areas, your weaker areas, and that will give you a really good idea of where to focus your studies. In terms of which one to take as a sample test, I would probably recommend one of the more recent ones, 2001 or 2008. Though they haven't changed much, those two probably do most closely resemble the current format of the test. Okay, so I said this once, but I will repeat it. You want to be fully familiar with the format of the test, and in particular, you want to be fully familiar with the bubble sheets, the multiple choice bubble sheets. So you don't want to be wasting time when you get into the exam proper, finding your way around that. So again, make sure you've looked at this very carefully. The questions themselves, the 100 that I mentioned, are ordered essentially randomly by topic. You will find in any typical test that there are a small number of grouped questions that have to do with a similar setup. But aside from that, you're going to see that they're essentially randomly ordered. And we're starting to get into some of the sort of tips and strategies that will help you, given that you've only got 1.5 minutes per question. Some of the things that I think you will inevitably find useful on a particular exam, trying to get to the answers quickly in terms of maybe dimensional arguments, order of magnitude estimates, and limiting behaviors. Those 3 strategies are all very helpful. In some cases, of course, you can get to an answer by doing a somewhat lengthy calculation, but you don't have time. So you're going to want to resort to some of these tricks in some cases. And we'll see what that looks like when we get to some of the sample problems. A good strategy, as with more or less all exams of this type, I find, is to make a first pass answering those questions you feel good about, and then return as time permits for a second or third pass, and do as much as you can on those following passes. So what about the detailed format of the problems? So they are 5-option multiple choice questions. All questions carry equal weight. If you don't answer a problem or you give multiple answers, it's not counted. However, you should be aware that if you answer incorrectly, 1/4 of the number of incorrect answers is deducted from your overall score. And again, that's a fairly well-known sort of scoring scheme for multiple choice problems. And if you think about how that impacts your strategy for test taking, random guessing may lower your score, but if you're able to eliminate just one incorrect answer, then you, at least in principle, come out a little bit ahead if you random guess after that. I won't talk about the actual scoring in terms of scaled scores. It's a little bit obscure how that works, and ultimately, you don't particularly need to worry about that. One very important comment at the end of this slide: make sure you don't wait until the very end of the 170 minutes to fill in your answers on the answer sheet. There is scratch paper in the exam booklet, but make sure you leave yourself plenty of time to fill in all of your answers, and don't run out of time and lose points just for that. Okay, this slide is a little bit busy, but there are a lot of, I think, hopefully useful pieces of information on here. I already talked about the first 2 items, past GRE exams and studying the format. Again, I strongly recommend you take 1 test under realistic test-taking conditions to give yourself a good sense of where you are. In terms of preparation beyond taking sample exams, I think your undergraduate textbooks are a pretty good place to sort of spend time on topics that you feel you're a bit weak on. And in fact, even what I would say is good knowledge of an introductory physics course at the level of Halliday. If you know all of that stuff well, you're already a good way towards getting a great score on the GRE. Some students find it useful to combine their own summaries of material. That sometimes appears in the form of what might be called a formula sheet. You notice I underlined your own there. What I don't find is very helpful in general is using other people's summaries. I think the act of producing your own summary information really helps you figure out what you need to know, and again, strengthens any areas of weakness. So I'd recommend not being tempted to take other people's cheat sheets, but rather to compile your own if you find that's a useful exercise. In terms of commercially available prep materials, I don't find that much out there is particularly useful. There is a relatively recent new addition to materials that is available, and it's a book called Conquering the Physics GRE by 2 MIT graduate students. You'll see the name up on the slide there. That one I think is reasonable, and in fact on the next slide I think it is. I'll probably make another comment about that. One thing I've learned over the past few years that is also quite helpful and may seem a bit surprising is the AP Physics C free response problems are actually kind of in many cases at the right level. Obviously they're not the appropriate same format, but they are about the right level. And an insider tip may be one of the authors of the Physics GRE is in fact also an author of many of the AP Physics C problems. So in that sense, there's some useful similarities. On the next line down, you'll see I've made a note about Case Western Reserve University. They put together a few years back a nice pack of some fun flashcards for GRE prep. There's about 200 problems. These days you can get them in electronic format for your smartphone. Just go to the URL that I've provided, send them a quick email, and they should send you the link to that. And it's kind of a nice thing that you can use if you're traveling you know, on the subway or the bus or anything like that. I'm a big fan of forming a study group. If you have peers at your home institution, of course, that's a good place to start. Conceivably these days, if you don't have that, you might be able to find a way to form a study group online. So if you can be creative there, I think that's very helpful. And you'll see down toward the bottom, practice, very, very important. You really want to have done all of the 5 sample exams and some of the supplementary resources I've talked about. There's a pretty good online site at grephysics.net that provides nice worked solutions for the 4 older sample exams. I don't think the 2008 one has solutions there, but it's nice that it has well-reasoned solutions. There's even a place where students can add their own alternate tracks to the answers, so that's a pretty nice resource. Okay, content. This hasn't changed much over the years, and I think it's still current. So take a look at the topics that occupy the biggest fraction of the questions on a typical GRE exam. I'm going to fold in the top 4 lines together. So classical mechanics at about the 20% level, E&M rounding to about the 20% level, quantum mechanics and atomic physics, which is really applied quantum, again at about the 20% level. So if you fold those 3 topics together, you're already at about the 60% level. That might give you some hints about where to focus your study time. And then topics that come in at smaller levels, so waves/optics, maybe 10%. Thermal statistical, again around 10%. And then some smaller topics, relativity, a few percent, what they call specialized, and that typically means nuclear particle condensed matter, and lab methods, which is always a little bit of a ill-defined topic, but does include statistics. And you'll probably find on a given exam there will be 1 or 2 questions on simple statistics. And I'll come back in a moment and talk about materials that might help you present for those last 2 topics, the lab methods and specialized. Okay, I mentioned some textbooks. So to my taste, a good intro physics book is going to get you a good way to where you need to be. I picked Halliday here, but there are others. In terms of somewhat higher, let's say intermediate level texts, again, I won't go through the complete list. Many of you will have used many of these books. But I want to quickly jump down to the last bullet here, which is the special topics and lab methods. You see here that I wrote no obvious suggestions. You might be able to ask a local faculty member at your institution to try and give a short review on that. And in fact, if you don't have somebody who's already doing that, you know, make a sort of appeal for somebody at your institution to see if they can organize a review session overall, because that, of course, can really help you in your studies. But the lead comment I want to add there is that the understanding the Conquering the Physics GRE textbook by the 2 MIT grad students is actually probably a reasonable place for summary material on those special topics and lab methods. So keep that in mind. But at the end of this slide, I do want to encourage you not to spend too much time with books. I think it's a good way to go if you're reviewing things you're unsure of or helping to compile your own review summaries. But what I think is not useful is to spend all your time, reading through chapters and necessarily working through problem after problem from your textbooks. I don't think that's the best place to spend your time, at least not until you've done all of the other things we talked about. Okay, so practice, practice, practice. You definitely want to start early. Those of you who are taking the exam this fall, I hope you're well underway already. If you're not, please make sure you get started as soon as possible. I find it's extremely important to set yourself a schedule, probably ordered by topic, and stick to it. So you might have a particular week on E&M. You're going to review, maybe do all the problems on E&M on the 5 sample exams. Obviously, that'll highlight any weaknesses, go to your textbooks, talk to your friends, and strengthen those areas of weakness. But stick to that schedule. Super important, and you don't want to be cramming at the last minute. So probably one of the most important recommendations I have. Okay, so that's sort of a fairly speedy run through some recommendations. I'm going to hold off on questions for a little while and instead jump to some practice problems. What I've chosen here are, in fact, the first 10 problems from the 1986 sample exam, and I'm just going to propose going through them in order. And I will talk through these to some extent, and then we'll open it up after we're finished for either specific questions on these problems or general questions about preparation strategies overall. So here goes. Okay, so this is the 86 exam, and again, they're randomly ordered. So here is the first problem. I'm going to let you all read through this. I obviously am not going to give you a huge amount of time, but it has to do with a rock thrown, and we're told some of its initial parameters. We're also told there's a friction force acting on the rock. We're told we can neglect buoyant force exerted by the air, and then we're asked to say something about the motion of this rock. Okay? So take a look at the question and take a quick look at the answers. And again, we don't have time to go through this in great detail, but what I want to talk you through is some of the strategies that hopefully will help you get to an answer quickly. All right, so we're told we can ignore the buoyant force. Of course, there's a force of gravity acting on this rock, and since it's presumably a near-Earth problem, we're not expecting this rock to go very far. We can assume the force of gravity is essentially a constant, mg. So we're asked to say something about the motion, okay? So when I first look at this, I see first possible solution. We're told that the acceleration of the rock is always equal to little g. So it's a constant. And I immediately look at this and say, that can't be right, because I know there's a gravitational force, but I also know there's a velocity-dependent friction force. So I assume that the acceleration, just making use of Newton's laws, cannot be constant. So I can immediately exclude that answer. Okay, then what else do I look at? The acceleration of the rock is always less than g. Well, maybe not so immediately obvious, so let's hold off on that one for a while. Let's take a look at D and E, and it has to do with speed of the rock upon its return to its starting point or attaining a terminal velocity greater than its initial velocity. When I look at those two possible answers, I immediately think of energy conservation. And the fact that we've got a friction force, so non-conservative, we know that we're not going to be conserving energy here. And so sort of carrying that a little bit forward, I immediately conclude that D or E is not the right answer. So again, I'm not going to go through fully working these things, but what you'll hopefully be able to conclude for yourself with eliminating obviously incorrect answers is that the correct answer in this case is that the acceleration of the rock is equal to g only at the top of the flight. And you might have time, and in fact you probably would, to write down the equation of motion here, F equals ma, and you know the two forces. Just make sure you've got your directions of those forces set up with a consistent coordinate system, and you'd quickly find, as expected, that you get the acceleration of the rock equal to g only at the top of the flight, because that's where the velocity is 0. Okay? So there's the first problem on the 86 GRE done. Let's move on to the next one. This one's a little bit more tricky to my taste, and it actually deals with a topic that appears not infrequently on the Physics GRE, which has to do with shapes of orbits of things where we've got a central force. So things like satellites, planets around a star, something like that, central force problem. And this is a pretty good example of it. So we're told that we've got a satellite orbiting the Earth in a circular orbit, and this satellite has somebody on board, and we're told that this person perturbs the orbit slightly by briefly firing a control jet aimed towards the Earth's center. That sentence turns out to be, requires a little bit of careful parsing. And so the first thing that I was a bit confused by when I read this is it says firing a control jet aimed towards the center of the Earth. So that actually means that the rocket exhaust, if you will, is headed towards the center of the Earth. And so we're essentially applying a force that's outward, radially outward from the Earth's center. So that took me a while to make sure I understood exactly what's happening there. And then it turns out that the word slightly is going to be important here as well, and we'll see why in just a moment. So then we're asked to select which possible orbit describes the motion of this satellite after that rocket has been fired briefly. So I mentioned these central force problems are fairly common, and hopefully you'll all remember some of the possible orbit shapes we can get in central force cases like this. And what you may remember is that they're all essentially conic sections. So that means we're looking at circles, ellipses, parabolas, and hyperbolas as possible orbits in central force problems. And in fact, if you remember how those are ordered, it's essentially in terms of increasing energy. So we can start out with the lowest possible stable orbit in a circle. We add a little bit of energy, we get to an ellipse. Both of those are closed orbits. We add more energy, we get to a parabola. Add more still, and we get to a hyperbola, those latter two being open orbits. So that's something to think about. And then a couple of options down here we should probably take a look at. Circle with larger radius, spiral with increasing radius, exhibits radial oscillations per revolution. All right. So how do we get to the right answer, which I should say is A. It's an ellipse. Well, what we're doing is firing this rocket, so we're adding a little bit of energy. So in a sense, we're trying to push the satellite to a little bit larger radius orbit. And the next highest energy orbit shape turns out to be elliptical. And this is where I think the word slightly is so important, because if we added a lot of energy to the orbit, we could, in principle, go to the parabolic and hyperbolic orbit shapes. But we're only adding a small amount of energy by firing the rocket briefly. So of A and B, A would be the preferred option. Circle with larger radius. Well, again, circle is pretty much only the only scenario we have for this lowest energy stable orbit. Anything higher energy than that becomes elliptical. Spiral with increasing radius, maybe. If it was firing continually, then we might expect the radius orbit to be increasing, but it's only firing briefly. And we certainly shouldn't expect radial oscillations, and there are several reasons why you can think that's the case. So not as straightforward in this case, but hopefully with the sort of lines of reasoning I mentioned, you can fairly quickly get towards the answer that we're an ellipse. Okay, next one. So this one clearly has to do with wave propagation. Again, a quick look at the problem will tell you it has something to do with wave propagation velocity. And we're told something about light traveling through a medium which has a permittivity, a relative permittivity, and a relative permeability. We are given that the light speed in vacuum is c, as usual, and we're asked to say something about the velocity of propagation of the light, aka the phase velocity. Unbounded, so we don't need to worry about any edge effects. So what do we do here? Well, first off, when I see this, I might sort of think about the standard wave equation. Unfortunately, I can't easily write things in the format that we have here, but you'll all hopefully remember the standard wave equation. And that wave equation includes the wave propagation velocity. So in the case of electromagnetic waves in vacuum, one thing you'll hopefully recall from your intro E&M is we can relate the velocity of light in vacuum, c, to the permittivity of free space and the permeability of free space. So that means epsilon 0 and mu 0, respectively. And you might recall that the velocity of propagation is equal to 1 over the square root of epsilon 0 times mu 0. Now, in this case, we're obviously in a medium. which has relative permittivities and permeabilities. So in this case, we expect a modified and, in fact, lower light propagation velocity. And again, just going back to your intro E&M, you'll remember now that the velocity of travel is simply equal to 1 over the square root of the absolute permittivity times the absolute permeability. So this is a bit of a mouthful, but if you put this in terms of relative factors, you'll see that that gives you v squared, if you will. The propagation speed is 1 over the relative permittivity, namely 2.1, times the relative permeability, 1. So take those two factors together, we get 2.1. So we've got v squared equals 1 over 2.1 times c squared. Take the square root, and we find that v is 1 over the square root of 2.1 times c, namely option D. Okay, so that was not the easiest thing to explain without being able to write this up on a board, but hopefully you followed that pretty nicely. And one thing you should immediately see looking at this, we're in a medium, so the velocity's got to be less than c. Immediately rules out A and B, and if you're having trouble after that, you might say, well, random guessing of 1 out of 3, my odds are good there, but hopefully you'd also have time to figure out the actual answer D in this case. Let's move on. So, number 4, waves again. We're given a wave, a propagating wave equation here. It gives an amplitude y in terms of a time t and a, let's say, displacement x. So that should look fairly similar, fairly familiar to you. And may look a little bit different than a form that you perhaps are most familiar, which is to say in terms of a wave number and an angular frequency, but otherwise it looks rather familiar. Remind you that the wave number k can be expressed as 2 pi over the wavelength lambda, and the angular frequency is just 2 pi times f. So you might be familiar with seeing a sort of traveling wave expression that looks something like y equals a sine parentheses omega t minus kx. So a traveling wave. All right, let's see if we can figure out which of the following options is correct. So again, I look at this and see which ones I can quickly exclude because they're obviously wrong. A falls into this category. Amplitude is definitely not 2a. Our amplitude is defined as the maximum displacement, so that would be a in this case. Velocity is in the negative x direction. Well, that doesn't seem right either because I've got a negative sign before the x term, and if you remember your standard traveling wave prescription, that represents a wave traveling in the positive x direction. So those first two options I've ruled out. Then we've got a few possibilities which I don't know how plausible they look, but we need to eliminate them. And in this case, remember that the wave travel speed we can express for any traveling wave as being the product of the wavelength and the frequency. Well, I don't see an f in there, but I do see a lambda. And what you also know is that the frequency can be expressed as 1 over the period t. So if you look down at the options there, that last one, E, seems correct because 1 over t is equivalent to the frequency. So now I've got frequency times lambda, that's the wave travel speed, and E is the correct answer. Okay, well, let's move on. So number 5, again, a mechanics problem. This is one that I don't find a fast way to get to an answer, so there's no shortcut other than doing the calculation. But take a look at what it's describing. We've got a pendulum. It's initially held off to one side. This is object A. We're going to let it swing freely. It's going to hit object B. They stick together, and then the combined object swings the other direction. So what's going on here? If you look at that, I would say hopefully you'll think of essentially 3 successive parts of the motion. What does that mean? As A swings down, I'm immediately inclined to think of energy conservation. As A hits B, they collide, they stick together. I'm inclined to think of linear momentum conservation. And then as that combined object swings up the other side, again, I'm inclined to think of energy conservation. So hopefully that sort of chain of reasoning is one that seems natural to you. If you do that, you're going to have to do quick calculations of energy conservation, first part, linear momentum conservation, second part, and energy conservation again in the third part. I don't have time to go through that, nor is it easy to do just in words, but you can easily find this work through. And folding those three things together, you will find that the answer for the height to which this combined object rises is h0 over 16. Okay? So again, in terms of strategies here, look at the possible solutions. They're all multiples of h0 that are less than h0. All of those, of course, physically make sense. So you actually have to do the calculations in this case to get to the right numerical prefactor, which is 1 over 16. So no shortcuts in that one. Okay, let me do a couple more and then we'll stop and open it up for questions. So problem 6, this one's an interesting example of limiting behaviors as a good strategy to get to the answer. So again, take a quick look at this. We're told that a particle is initially at rest at the top of a curved frictionless track. We're told with the coordinate scheme given that we can say y equals x squared over 4. This particle's sliding down the track, and we're asked to say something about its tangential acceleration. Okay, so this is one that when I look at this, again, a little bit based on experience, I'm inclined to think of limiting behaviors as a good way to get to the answer. Do I expect the tangential acceleration in this problem to be constant? No. The slope of this thing is varying. It's presumably experiencing the gravitational acceleration downwards and some variable fraction of that as the slope varies. So it certainly isn't constant. I'm going to rule out A and B based on that. So I've got C, D, and E left. What about limiting behaviors? What do I expect to happen as I go to very large x? Think about it. If I go to very large x, we're asymptotically approaching the case where y goes to infinity. So it's essentially becoming a vertical curve. And if it, in that limit, becomes a vertical curve, I'm expecting that in the limit, the tangential acceleration should go to g. So of the remaining options, C, D, and D, just do some plugging in as x goes to infinity, see if we get to the tangential case of having the limiting acceleration be g, and the answer that gives us that is D. Okay. Again, you could calculate this, but you don't really have time to do it in terms of looking at components. So this is the case where limiting behaviors are really going to get you where you need to be. So let's take this one perhaps as our last worked example for now, and we'll see how we do time-wise after some questions. So this is the 7th problem, and if you take a look at this, again, some setup information on the right-hand side. Take a look at the sketch on the left side. We're told that this is a static problem, essentially. So, of course, it's a statics problem, and we're told it's in equilibrium. No particular shortcut here, really. Take a look at it. You're looking at balancing forces, and obviously the easiest way to do this is balancing forces horizontally and vertically. What do we need to worry about? Well, I see 3 forces acting on that block. I see a horizontal force, constant magnitude, pulling to the right. I've got a vertical gravitational force, constant magnitude, pulling downwards, and presumably there's a tension force in that string that's keeping everything in equilibrium. So what you want to do here is resolve that tension force into components, horizontal and vertical. Do the balancing, because it's a static setup. Get 2 equations based on Newton's laws for zero acceleration in the vertical and horizontal direction, and then solve those 2 simultaneous equations. And if you do that, you will find that the answer, the angle theta here that we're looking for, is the inverse tangent of 0.5. So I know don't want to go beyond our time here and want to leave plenty of time for questions. So I'm going to stop here, hand this back to Crystal, who's going to moderate with questions, and we'll try and address as many of those as we can.
All right, great. Thanks, Jeremy. Yeah. Okay, so I'm getting a few responses about the specific problems, but actually most of the questions that I'm getting pertain to sort of the earlier part of the broadcast. So I'll start there and kind of keep an eye out. If you guys have specific questions about the problems that we just did, you can also type those in. Okay, so the first one, going way back to the beginning, you said that it's possible for students to take the exam multiple times and then use score select to decide which scores gets into which institutions. And I have a question. When they take the exam multiple times, will the test be the same, or would they expect them to be different exams?
So it will definitely be different each time.
Okay, great. That explains that.
Short answer.
Okay. So another question was if if you could say more about the lab techniques section, to what extent will error analysis be involved in that? And actually, could you say a couple of words about how to prepare for those kind of stranger experimental techniques sections, those more esoteric sections?
Yeah. So that's a tricky one. There's sort of, I mean, the number is few, so it's few enough that you can't sort of deduce any particular theme or focus. What I think I can say is that you can be sure there'll be something about statistics. So not necessarily error as such, but there'll almost certainly be something that has to do with simple distributions, whether it be a Gaussian distribution, possibly a binomial distribution, maybe Poisson. Even there, I'd say Gaussian is the one that's most likely to come up. And I've certainly seen cases where probability also might appear. And so, for example, where might we see a physical problem that involves probabilities? Natural radioactivity, decay rates of some radioactive nuclide, and maybe it's a nuclide that has more than one possible decay channel. And it might be a case of, let's say, we know a decay rate for one possible channel and a decay rate for the second possible channel. What can we say about the decay rate overall, or the probabilities of a decay within a particular time interval? So in terms of prep, I would say, first off, you don't want to spend a huge amount of time on this. The number of questions is going to be small, so don't weight this too much. But if you are spending time on it, I'd say a review of simple probability and statistics is your first priority. In terms of actual lab techniques, it's totally random what might appear here. I've seen something on one of the practice exams which it would be impossible to prepare for, I think, which have to do with what would happen if you put in two signals on orthogonal axes of an oscilloscope. And some of you may know that can give rise to what's called a Lissajous figure. How would you ever predict something like that would come up? You couldn't. So I would say don't waste your time trying to guess what might come up. The GRE book by the MRT grad students would be my last recommendation there. They have a little bit of stuff on lab techniques. That's the best sort of concise source of information, I would say. But to reiterate, don't stress about it.
Okay, great. Another thing I just want to address really quickly. I'm getting a lot of questions that are very similar, sort of along the lines of how do I know what minimum GRE score I should make? How does that figure into whether or not I'm accepted to a graduate school? And I actually want to just break in here quickly and say a really fantastic resource is gradschoolshopper.com. What that is it's basically a database of most, if not all, of the graduate programs in the U.S. And they basically give a very specific set of requirements that are needed, including minimum GRE test scores, GPA, other kinds of things that are necessary to have on your applications. And it also gives a summary of the program's primary research focus areas. You can search on things like location and research area, all kinds of these parameters. You can do a search, and it's pretty exhaustive. So it really is a great resource for answering those kinds of questions. And Jeremy, do you have any other advice?
This is a sort of fairly complicated topic, obviously, and there's no easy answer. So let me sort of say a few comments. I think in terms of being a strong applicant for a graduate program in physics, there are sort of three components that are important. A good undergraduate transcript, so obviously you want to do as well in your physics and to some extent math courses as possible. That's a very important ingredient. The Physics GRE, in a sense, backs that up, and in cases where you're maybe at an institution that is not well known to the people on the admissions committee at the schools you're applying to, it sort of acts as a sort of normalization or calibration point, because they may not otherwise know exactly how to interpret your transcript and grades because they may not know your school well. So that's important, doing well as you can on the Physics GRE, obviously. But I would say as important, maybe even more so, you know, these days as you're applying to physics PhD programs, a lot of schools are looking for you to have had some prior research experience as an undergrad. So if you have opportunities to do that, I strongly urge you to take advantage of those, whether they're at your home institution or in the summers at another institution, maybe through the NSF-sponsored REU programs. But prior research experience is increasingly viewed as being an important component of your application. And what comes along with that very often are good letters of recommendation. So you want to be working on prepping and essentially sort of prepping the people who are going to write letters for you early on. Make sure that they are involved in your grad school application process. Make sure you keep them up to speed on that you tell them where you're applying. They may have good advice for you, whether it's about your application generally or good schools to apply for that are good matches for you in your areas of interest. You really want to cultivate those people and let them know well ahead of time that you're going to ask them to write letters, because those letters are really important. And what do I mean by this in the context of the Physics GRE? What range of GRE scores a particular school or program accepts? It's very hard to say anything quantitative on. Obviously, there's a correlation with what you might call the sort of renown or prestige of a particular school. But having said that, you know, a school that's quite competitive may well accept students with a lower GRE score if the other components of our application are particularly strong. So if your GRE score isn't great, but you've got great letters from the research you've done in a particular faculty member's lab, that will go a long way. So it's a complicated sort of set of inputs, and again, very school dependent. So I'm always reluctant to kind of say what's a minimum GRE score that you need. I don't think such a thing exists. Depends on where you're applying. And the other thing is, I guess, maybe just a couple of other footnotes and then I'll stop. I think some schools probably take physics GRE score as at a sort of soft level and at a relatively low score, a sort of first pass cut on applicants to their program. But usually it's only a very soft cut, if at all. And then after that, they'll basically look more closely at transcript and letters. So it's a kind of soft threshold. And that's, to some extent, how I think I'd recommend people view it. Obviously, you want to do as well as you can, but it's by no means the sort of be-all and end of all of your application. The other things are perhaps even more important. And I'm often asked at this point about the general GRE score. Most physics departments, in my experience, do not pay much attention to the general GRE, though they all pretty much require it. But in general, they don't tend to pay a lot of attention to that. That's not to say you should blow it off and not do as well on it as you can. But really, the physics GRE is the thing to concentrate on.
Yeah, and if it helps any of you guys, for me to mention this, I'm nearly 40, so I can admit this to the world, that I failed utterly. My physics GRE failed. I had no access to these wonderful resources such as your expertise, Jeremy, and I still went to a graduate school, and I still got my PhD, and my life is still okay. So, yeah, just wanted to share that.
Yep.
Okay, but just to clarify, like you said, you do have to take the general. You're just saying they're not going to look at that score and say, oh, well, you know, that means something.
That's my sense of all the schools and people involved that I talk to. Once in a while, and it's worth, you know, researching the institutions you're interested in, of course, and you want to do that. You have to do that before you submit your application to tailor it for that institution. But you might find occasionally an institution that is trying something a little bit non-standard in terms of its admissions process. So, for example, I've once in a while heard of an individual institution that has not taken that approach, and in fact, they've maybe looked quite closely at the GRE, the general GRE. So you have to take that advice with a little bit of caution. What it leads me on to say is there's no substitute for learning as much as you can about a particular institution you're applying for. Talk to faculty at those institutions. Talk to, if you can get access, current grad students at those institutions. But most faculty are quite welcoming of inquiries, let me say informal inquiries, outside the formal application process. So think about that as you're looking at schools. It's not, it's certainly possible to ask questions informally, and that's usually a good way of learning more about the particular sort of opportunities available, which faculty are working in which subfields, and so on and so forth. I will agree with Crystal that grad school shopper resource is very useful, has a lot of quantitative information, but again, there's no substitute for talking to real live people at many of these places to get the scoop on what the programs are actually like.
Great, yeah, okay, excellent. Gosh, there's so many questions. I'm trying to kind of keep them all straight. So the next question is, I've had several people asking who are non-majors in physics and are taking the Physics GRE exam. Do you have any particular advice for them as to how they might prepare for the test?
So, couple of thoughts, I guess. If you're applying to physics PhD programs, which maybe you're not in all cases, but if you're applying to physics PhD programs, I think to some extent the fact that you're not a major in physics, but let's say minoring in it, is not really significant. People in general in admissions committees are not looking to see whether it says major explicitly, but what they're looking at instead is to see that you've covered most of the sort of foundational topics in your undergraduate coursework. So while you may not have a physics major, maybe you have a physics minor, and you've taken, let's say, 80% of the physics coursework that a typical physics major would take, that's fine. You may want to just be clear and make sure that's highlighted in your application. But again, I think admissions committees are looking to see your grades on those sort of core physics courses. If you happen not to have one or two of those core courses, and I can tell you from my experience here, very often we have people applying to our PhD program that haven't taken undergraduate thermal and stat phys. Generally, that's not a big deal. People recognize that some schools wouldn't be able to offer that or other reasons, and they'll make allowances for that, and they'll simply ask you to take that course once you're in the program. So that's one sort of set of comments. In terms of prep, otherwise, I mean, obviously, if you haven't taken courses in some of the important topics on the Physics GRE, you're going to have to do self-studying there. No easy way around that. I would say it's tough. I mean, you kind of need to have got at least the basics. I'm thinking of quantum mechanics here. Most people will have done a sort of intermediate mechanics course, intermediate E&M course. They will not have done a sort of full rigorous quantum mechanics course. Since ultimately 20% of the problems on the GRE are going to be on both pure and applied quantum, you kind of need to have covered that material at some level somehow. And of course, you can tell I don't have any great advice how to do that. The other possibility is, just make it clear that if you're from an institution that hasn't been able to, offer you a course in a particular subject, you still take the Physics GRE, you do well on all the topics that you have covered, but make it clear in your applications that, that particular course wasn't available. So of course you don't know the material. Therefore, your Physics GRE score is down a little bit, but just explain that. I think if you're clear about explaining it, people will, again, make allowances for it.
Okay. Another question. Did I already ask this? Oh, if you take, if you take the exam multiple times and you do significantly better the second time, is it better to send both scores to show improvement or just the higher score?
Interesting question. I would say just send the highest one. I mean, does it count for much? Probably not. But I think just sending the highest one, I guess the way I'm thinking of this, not that I think many admissions committee members would borrow this deeply, the fact that you're showing a lower score, they might just look at that and think somewhere in the middle is what's actually a reflection of your ability, or I don't know what they'd think about it. I guess there's nothing gained, I think, from sending both. I think my recommendation would just be to send the highest.
Okay. And then speaking of scores, I've also had several questions about the percentile versus the raw score. Can you say anything about which one would be more meaningful to graduate admissions? I mean, how are those two pieces of information digested?
Yeah, I think this is a strange thing. Frankly, I'm not sure many of us understand how this happens. But I think what I can say just from our admissions process here, we only look at the scaled score, so not percentile. The ETS folks each year, depending on the absolute difficulty of the exam, I guess they curve these distributions. And again, it's never fully clear, I think, to people in physics PhD programs how that works. So we just go with the scaled score, and that's, as far as I know, of most places, the only piece of information that we look at.
Okay. Okay, very good. I have another couple questions from folks who are actually international students. One was a student who is in Puerto Rico, and they actually they wanted to make sure that they understood where they might go, how to know where to go to take the exam. Is that information on the ETS website? So that's one question.
Yes.
And then the second one is, does it matter which time they choose to take the exam?
Okay. So I don't have really any experience with international test takers. I do know that the ETS site has a special link right below the link for domestic test takers in terms of dates for the exams. So if you go to the ETS site and just click on schedule or dates, you will find a link there for international test takers. I assume there is also a list of approved test-taking sites there. I'm sure there is, and if it's not online, which I'd be very surprised about, I would imagine a quick email to ETS will get you that information. In terms of when, in terms of being as well prepared as possible, this obviously will depend a little bit on individual circumstances. Our students invariably kind of tend to gear their prep towards usually taking the second test in the fall of senior year. So that's now October. And that's sort of, in a sense, it's the latest one possible to still have results in time for the application cycle for the following school year. So that's usually the sort of target test date. Having said that, and I mentioned this early on in the presentation, I think there's quite a lot of value in taking certainly both of the tests in the fall, so September and October. Gives you two shots at things while you're both, in both cases, pretty well prepared. And in some cases, obviously finances may be a consideration here, but in some cases, if you feel you've got enough coursework under your belt, maybe even taking it in the spring of junior year, just in the spirit of fully familiarizing yourself with the whole experience, getting maybe some nerves behind you, and of course a third taking gives you one more shot in terms of your score. Not many people can afford to do it 3 times perhaps, but keep all of those considerations in mind. Most people don't benefit from doing it any earlier than spring of junior year just because you haven't typically taken some of the coursework that's going to appear on questions on the exam. So I don't think there's any value in doing it sooner than that. Standard thing would be to take it twice in fall of senior year.
Okay, great. All right, so really quick, I just want to make a quick announcement. We are basically out of time for the official webinar. However, for those of you who are interested in sticking around for some additional questions, there are lots. We are going to stay on the line and actually answer some additional questions. Just as a reminder, though, this session has been recorded, and everyone who's registered will receive a copy of the recording. If you do have to leave now, we apologize if we were not able to answer your question, but you're welcome to follow up by emailing webinars@aps.org, and we can forward your question along. All right. So thank you, Jeremy, very much, and let's get back to a couple of additional questions. So some folks are asking, first of all, have the exams changed much over the years? This really has to do with finding a source of practice problems. So if you go back to many, many earlier exams, will those be significantly different than the one that students are likely to take this year, A, and B, are there additional sources for practice problems besides those earlier exams?
Yeah. So my sense is there really has been, I mean, maybe not surprisingly, but there's been very little change over, those 5 sample exams that you all have access to. There's a variation in difficulty, I think, and this a little bit relates to the sort of scaling of percentile versus scaled scores. So there's a little bit of variation in difficulty among those sample exams. I wouldn't say it's a huge factor. There's some indication that in recent years, the Physics GRE hasn't included problems in recent years where a simple look at units associated with possible answers will get you to the answer, to the solution. If you look back earlier on, there were sometimes cases where you would have different possible answers to a problem where looking only at the units would help you. That seems to have died down some in recent years, though I don't think it was ever a particularly large component. I still find that dimensional analysis is very important. I don't see that that's changed much. And those tips, other tips that I mentioned, limiting behaviors, all of that, to my mind, has stayed pretty constant over the years. And if you ask students who've taken the exam in the past couple of years, anything striking, I've never heard of anything. So punchline is, I don't think it's changed much. In terms of additional problems, so I think the MIT book, Conquering the Physics GRE, I think they have some additional problems that are very similar in style. And beyond that, not really. I think I wrote in my slides early on, though it seems like it wouldn't be relevant, and certainly in terms of format, it isn't relevant. I think the material in those AP Physics C free response problems is pretty good. It seems about the right sort of style, even though it's not the same format. So those would be my recommendations.
Okie doke, great. Also, there are several questions. Okay, first of all, this is just an interesting question. Is it useful to take the Physics GRE if you're not planning on going to grad school in physics?
So the follow-up question has to be, but doing what instead?
Right, right. Okay, so
it's, the Physics GRE is required for some Astro PhD programs for sure. The one scenario I can imagine suggesting you take it is if you're unsure whether later on you might want to apply to grad school and maybe you want to try something else out for a while, which a lot of students do. My advice there would be to take the GRE on the usual schedule, obviously do as well as you can. And I think there's a sort of 5-year limit on the formal validity of your GRE scores. But obviously, you're going to be better prepared in general to do it at that time. So, as you're wrapping up your undergraduate degree, rather than trying to come back a couple of years later and refresh yourself on all of that material, if you decide you want to come back and actually apply to grad school. So that's certainly a scenario I see quite often. And if you're in that case, in that situation, I'd say, yeah, sure, do the Physics GRE when you are most familiar with the material. You can bank that if you eventually decide you are going to apply to a PhD program. But otherwise, I'm not aware of any other sort of career track or any other vocation that they will really ask about Physics GRE.
Okay. Well, and a kind of a related question I've gotten from several folks, if you're talking about a program, for example, biophysics, that takes both bio and Physics GRE scores, would it be more competitive or more impressive if they took the GRE, the Physics GRE versus the bio GRE?
Okay. Interesting question. I suspect that's pretty strongly dependent on the program at a particular school. So, you know, if I just look at my home institution here, our particular biophysics faculty, I would say, are somewhat more on the bio side of things than on the physics side of things. And I think that's inevitably going to sort of factor into their considerations when they're doing admissions. So I think that's the answer there is it's a school-dependent question. You know, some schools may be doing biophysics that's more physics-oriented, and then they would probably be more interested in the Physics GRE. So I know that's not a very helpful answer, but it just reinforces the sort of message that you do want to research schools that you're applying to and make sure that you sort of tune or match your application as best you can to that particular school's program.
Mm-hmm. Okay. Another question that is interestingly only just now come up, is there any sort of statute of limitations on the scores? How long are they valid? How long might they impact you?
So I think that's the 5-year figure that I quoted. I must confess I'm not 100% certain on that, but I believe, at least in our grad school, I think they allow up to 5 years. So that's a sort of formal answer. I should say that, you know, if it's really 5 years between you having taken a Physics GRE and you applying to PhD programs, I think an admissions committee will have other types of sort of pertinent questions, perhaps more than your Physics GRE score. Namely, you know, they'll be wanting to know what you've been doing in that intervening period and make sure that you have a story, if I can use that word, that makes sense, and that they, you know, they believe you're a viable candidate for a PhD program. But I think it's probably, again, graduate school dependent. I kind of feel here it's 5 years. Okay,
that definitely answers the question. Maybe we'll do a couple more. They keep flooding in, which is great. But several people have also asked about situations where, for whatever reason, they'll be taking the exam before they've actually had 1 or 2 really crucial courses, for example, thermodynamics or maybe quantum or E&M, which maybe they've only had part of their semester of E&M. What advice would you give to folks in that situation?
Yeah, so it's a balance. I think you want to have tried to schedule your coursework so that you've taken courses in, you know, I'm picking a number here, but let's say, you know, 3/4 of the main subfield topics that are appearing on the GRE and that you would be expected to have done as part of your undergrad program. So, you know, out of, let's say, an intermediate or advanced courses in classical mechanics, electromagnetism, quantum mechanics, thermal and statistical physics, I kind of feel you're going to struggle if you're missing 2 or more of those. You know, you'll have a hard time on the GRE, but also, you know, depending on a particular admissions committee, they may just think you need more undergrad prep before you're a viable candidate for a PhD program. So I think, you know, there's a limit to how little, in a sense, you need to have covered in terms of prior coursework. But if it's at the level of, you've never had a chance to take a thermal-stat phys course, or you've never, maybe you've had a one-semester course in quantum mechanics, but never got into sort of atomic physics, which wouldn't be unusual. Either of those scenarios I think is fine. If you feel you can self-teach yourself some stuff, let's say the basics in those topics in preparation for the GRE, great. So that's never easy. And if not, I think it's, again, resorting to the strategy of just being very direct in your applications, saying, I wasn't able to take this for this schedule reason, or my school didn't offer this course, so of course I didn't have the opportunity. So while I haven't been able to take a course in this, I've still got great grades in all the other courses, and I've got a pretty strong Physics GRE score, modulo the fact that I hadn't covered this topic, and just spell that out clearly. And I think if people recognize that, that's just fine. They realize that plenty of students are in that situation. If you're admitted, you'll take the requisite courses to fill in those gaps once you're in the grad program. So I think the sort of spirit of being just totally direct and honest there is the way to go. But again, the flip side of it is, if two or more of those courses you haven't taken, it's going to be marginal.
Okay. Couple of other questions about the actual test-taking environment. One person asked, it seems like a pencil, you got these very specific things you can bring in. They were asking about, for example, earplugs or mechanical pencils. Are those forbidden? And then another person had asked who to contact about applying for disability accommodations.
Okay. So I will admit up front, I don't know really the answers to the first question. So I'm going to refer you to the ETS site, and I think they're pretty responsive if there's a question you have that isn't answered there. In terms of accommodations for disabilities or health-related things, there's definitely a section on the ETS site that covers that in great detail. So it's part of their standard setup. Of course, they're expecting students will request accommodations and should be granted them. So that's very much a standard procedure, and all of the approved testing centers are approved on the basis that they can make those accommodations. So all of that stuff will appear on the ETS site. Okay.
There are so many good ones, but let's do one more question before we kind of wrap up. So I guess, gosh, I'm torn. I guess the question I would ask is, what advice would you give for students who prepared very well for the material, they prepared themselves for the exams, but the anxiety of being in the room and being in the situation is so great that they just blank out, or who don't do well under time pressure? What advice would you have for them? I mean, I assume doing the exams in the real world situation as much as possible would be one recommendation. Is that right?
Yeah, I think that's the most important thing. That's where, for some people, I think, if finances allow and you feel reasonably prepared, possibly doing a trial run spring of junior year can be really helpful there. I have to be cautious when I say that. I mean, it's good because it exposes you to the exact environment you're going to be experiencing in the exam proper. So that's good. I think any familiarity obviously lessens anxiety. The flip side of that is you have to be careful not to take it if you're, really not some good way along to being prepared, because I think that might freak you out a little bit. If you're taking an exam and you're not prepared for it, that may have an adverse effect and it may make you more nervous. So that's something that is obviously a very personal choice. Yeah, it's difficult, and I'm asked this question in many different contexts, not just in the context of Physics GRE, but exam taking generally. The answers are so unique to particular individuals. I think, strategies like keeping to time, that 1.5 minutes or approximately 1.5 minute per minute goal, you want to stick to that. And you also, I think, it helps if you, on a first pass through the exam, only kind of answer those problems that you know on the first go through. Because I think the worst thing you can do is sort of get hung up on a particular problem that isn't working out, waste time on it, get all upset. If you find yourself in that situation, just cut yourself off. You know, that 1.5 minute, you haven't figured it out, forget it, go on to the next one. And kind of make sure that at the beginning of the exam, you're focusing on those problems that you know. So it kind of builds your confidence, you build momentum, and then you can come back as time permits and address those ones that are more tricky. So I would say, you know, if you're at an institution that has also just general, I don't know exactly what this office would be called at a particular school, but you know, most schools have resources that provide guidance, advice in some form for students in academic matters. And you know, they may have good suggestions for a particular individual about how to try and reduce those stresses and anxieties, and you know, specific strategies for individuals. So yeah, I think in summary, take a test under realistic circumstances. Don't do that when you're totally unprepared, because that will probably make you more anxious. And then try and stick with, let me say, tried and tested strategies when you're in the exam room. And if you know, in your case, things that work to calm you down, make sure you follow those strategies.
Okay, I think that's a good note to go out on, because certainly that's something that's probably on everybody's mind, and I know it was for me when I took it. So unfortunately, that is all the time we have today. So I want to say thanks again to our speaker, Jeremy Dodd, for sharing his insights, and to all of this wonderful audience for your great questions. Again, if you want to follow up, you can email webinars@aps.org, and you'll receive a follow-up email with a link to today's recording. Thanks again, everybody, and we hope to see you at our next webinar. Bye-bye.
Good luck, everyone.
Bye.